So let's get started. So what we're doing is we want to build a simple CPU. Okay, so we define a small subset of instructions that we want to implement, and we are actually going through basics of logic design. So the idea is we want to make some small like building blocks, and we're gonna put them together to make a simple CPU that can execute the y8664 ISA. Okay, that's the idea. So last time we went over the combinational logic. So if you remember, something like this, we can actually describe some like arbitrary combinational logic using a toy hardware description language called HCL. So this one is for example, on the left, upper left corner, we have a logic block that actually select one of the three input words, which is the smallest. So it actually takes the minimum of the three, and generates the output. The student actually pointed out correctly, this one actually should be like less than or equal, right? So please fix that. The right side, we actually show HCL, how we describe this logic block in C-like syntax. So that's basically how we use HCL. And on the bottom, we have another example of four-way multiplexer. It takes like 4 inputs, and depending on the value of a 2-bit like selection signal, one of the 4 will be taken. Okay, so that will be the MUX. And this one is ALU, arithmetic logical unit. It actually takes 2 input operands, like input words, like 64-bit words, and depending on the value of selection signal, like this function signal, selection signal, it will actually do some like different operations, right? If it's 0, it will do add. 1 it does minus, and if it's 2, it will actually do like a logical AND, and if it's 3, then it will be like a logical XOR. Okay, so it's kind of Swiss Army knife of the computation. So depending on the value, the input like a selection signal, it'll do something different. It could be add, sub. In general, in your real like a CPU, it actually does a lot more. You can actually provide a lot more complex computation, not just for, but you can do like something like or, not, and even like some like more complicated like operations too. So this one is another example of combination logic, because the output continuously changes responding to the input, right? And the control signal selects the function to be computed, and it corresponds to 4 arithmetic logical operations supported in y8664. Okay. Also, it computes the value of condition code. So it does not only compute the the value, the output. It also computes the flags. I mean, if there's carry, it actually asserts the carry signal. If it's 0, then zero flag will be 1, and so on. So these flag bits will be also set as a result of computation. Okay. All right. So now we move on to the storage side. So we actually so far we covered combinational logic. So now we move on to sequential logic to store 1 bit of information. This one is the simplest memory element we can think of. It's called cross-coupled inverter. So if you have a cross-coupled inverter, there can be 2 stable states, right? Either this node is 0 and this node is 1, or either this node is 1 or this node is 0, right? Because they actually cross-coupled, and output becomes connected to input, so that these 2 outputs will be always have the opposite polarity, right? If it's 1, the other is 0. If it's 0, then the other is 1, right? So they're always mutually exclusive. So this one is a very simple element that can store 1 bit of information. So if you we can see actually how this circuit works in more detail. Probably this part will be covered in more details in electric circuits. 전기 전자회로 과목에서 더 자세하게 다루겠지만 this part will be covered in more details in electrical circuit course. But the basic idea was, if you this inverter is implemented using two transistors, like NMOS transistor and PMOS transistor. So if you actually enlarge this one, if you see inside of this like an inverter, this one in fact looks like this. In transistor level, it actually has like a PMOS transistor and NMOS transistor. So this one is in, and this one will be out. Okay, and this one is VDD, I mean the high voltage, and this one will be ground. Okay, that's the inverter. So the way it works is, transistor is like switch, right? So this input value is like a high, like a 1. Then this one will be connected. If the input is 1, then this one will be connected. This switch will be connected, and this switch will be disconnected, right? If it's 1, input is 1, right? So this one, output voltage will be pulled down to ground. And if the input becomes 0, then now, this switch will be connected. This like a PMOS transistor will be connected, and this NMOS transistor will be disconnected, right? So this output voltage will be pulled up to VDD. So in other words, if input is 1, output will be 0. The input is 0, then output will be 1, right? That's the basically how this inverter works. So if you actually see the voltage, like a input voltage to output voltage curve, it generally looks like this. So if you the x-axis is Vin, this is the input voltage to the lower like an inverter. Let's say this is a Vin. And if you change your voltage from let's say 0 to 1 volt, let's say you sweep the voltage from 0 to 1 volt, then your output voltage, like V1, will be continuously go down, right? Because as you increase the voltage level, this like a switch, like NMOS transistor, will be more and more on, and then the resistance will become smaller and smaller. Eventually, this one is fully goes up to like a value of 1, then it'll go down to 0, right? So there's a relationship between Vin and V1, and as you see in this circuit, Vin now becomes input to V2. So the opposite thing will happen, right? Because as this one goes from 0 to 1, and this one will go to 1 from 1 to 0, and again now this one will go from like a 0 to 1, right? Because the output of the first inverter is connected to input of the second inverter. So the V2 curve will look like this, so red curve. So this one is a V2 curve, and what happens, we actually connect like these two. Let's say this output is now cross-coupled with the input of V1, like this. Then what's going to happen? Because in this case, now we actually short circuit these two nodes, like a V2 and Vin. There's another curve, looks like this. If you connect these two, like a V2 and Vin node, there's another curve, the blue curve, Vin, because the Vin and the Vin curve, this is just the same like identity function, right? There's a V into Vin, and this one's V into V2. So, but in this case, V2 and Vin should be actually identical. Right? They actually short-circuited, right? So there can be only 3, voltage level that can physically, feasible, physically like realizable. So this voltage, Vin, this V2 Vin voltage should be either in 0 volt or 1 volt or in the middle. There are only like 3 different like a physical, voltage level that this the relationship actually is satisfied. So this one is called stable 0. It's either like a stable 0 or either stable 1, or there's another condition called like metastable, like somewhere in the middle. So physically, there can be, it must be either of those 3 states. Either it should be the voltage level is always 0, voltage level is always 1, or somewhere in the middle. That's kind of only possible voltage level that this system, this like voltage node can have. So, but in practically, this metastable state is very unstable. So if you actually put, let's say, it's somewhat like you actually put your like a ball on top of the, onto the top of the mountain, or like a triangle, right? So theoretically, if you actually put your ball, drop your ball onto like a triangle, then it'll eventually either go down to this way or go down to that way, right? But in theory, with very, very small probability, maybe it can stay on top of the triangle, right? It's like, that's kind of metastability. It's very, very small probability, but it's non-zero probability. So, there can be either one of the three. This system will be stable in only one of the three positions, either 0 or 1 or like in the middle. But in this case, this like a metastable is more like, as I said, it's very, very low probability. It kind of, it's very easily disturbed. So practically, you cannot really stay that like a voltage level for a long time. So that's the reason why we actually, this register, this like a flip-flop, no, not flip-flop. This memory element is actually, can only have 1 or 0, but with like a very, very low probability of somewhere like a 1.5. But that's not really physically, the probability of this metastable state, the probability of this metastable state is very, very low. So it's practically, not feasible. Not feasible like a voltage level. So anyway, the important thing is, we can actually, make this very small, like 1-bit storage element using this, bistable element. Using like cross-coupled inverter. That's kind of, it serves as smallest memory we can build, and we use it as building block to make more complex, like, memory elements. So, you actually, if you put like a multiple flip-flops together, sharing the same like clock signal, and if you put them together, then they are called like a register. So this is like one of these things. This one is basically flip-flop, and if you put them together, and if you share the same clock signal and same control signal, that's called a register. You can actually put like some number of like bits together in the single register, maybe like a 64, maybe 32. That's kind of register, and this register is kind of this is what I mean by register here is a little bit slightly different from like program register, because last time we talked about program registers such as RAX, RB, RBX, RSI, all these things, right? Of course, these like registers are practically realized using this hardware register, but it's we sometimes need to distinguish the two, the program register and hardware register. So in this case, I'm talking about register. We actually what you learn from logic design course. Okay. Yeah. So and this one is collection of edge-triggered like latches or so-called flip-flops, and loads new value on the rising edge of the clock. And this is a symbol for register. So register works like this. So input actually comes in. Of course, there's clock coming in here. It's not shown, but clock is actually, it takes clock signal, and it actually stores data bits. And for most of the time, it works like a barrier between input and output, right? So even if input changes, the output is still, it's not disturbed, right? Output is still remain just constant. However, when clock rises, whenever there's a rising edge of the clock, new value will be loaded into the flip-flop, right? So value gets changed only at the rising edge of the clock, right? That's basically how register works. So if there's a rising edge of the clock, at that point, this new value of y will be loaded into the register, and the output will become y. Of course, after a little bit of delay. Okay. So that's basically in other words, the state of this register gets changed only at the rising edge of the clock, right? because the current like state of the register is basically its output value. So in this case, you can think of it as this register made a state transition from X to Y. So here is an example of a simple like a state machine, how we can build finite state machine using those components we have introduced so far. So here this one is flip-flop or register. This is a register, and this is MUX, and this is ALU, and this is very simple accumulator. Okay, so what accumulator does is at a new every clock cycle new value comes in. You basically add the new value to the existing sum of the value. Okay, so as you make a progress, this value gets accrued, gets accumulated to compute the sum of some like a number of scalar value. So here, let's say also there's like a load signal. If the load signal is 1, so if load is enabled, that means the input to this register is taken from this input value, like this, right? That means if load signal is 1, new value into the register. If this load signal is 0, that it computes the sum of the existing, like a sum of the value plus new incoming value, right? And this output will be the new input to the register. So in this way, if the load signal is 0, it keeps accumulating the value, incoming value. If it's 1, then you actually update this register with the new value. Okay. So here, it looks like this. Here's an example. So here, if it's a load value, this is clock, and this is load value, and this is input signal. Let's say x0, x1, x2 is some like a Scala value, like 64-bit value. Then if load is asserted at the rising edge of the clock, if load is 1, the new value from this input signal will be loaded, right? So at this rising edge of the clock, after a little bit of delay, this output value will be updated to be x0, right? Because new value will be loaded here. In the next cycle here, next rising edge of the clock here, the load signal is, that means it keeps accumulating the value. So it actually, the original value was 0, and new incoming value is x1. So it actually adds the value of the 2, x0 and x1, and then put the sum of 2 into the register value. So the new state will be x0 plus x1. In the next clock cycle, again, do the same thing. The new incoming value is x2, and load is 0. So it keep accumulating, x plus x2 plus x3. And then in the next cycle, actually in this clock cycle, the load value is 1. So now we actually load the new value into the register, reset the value to x3 and so on, right? So that's basically how it works. And you can actually put like multiple registers together to form a register file. Okay, it's a register file is nothing but like a small piece of memory, and it can store multiple words of memory. Let's say in our y8664 ISA, we define 15 registers, right? RAX, RCX, RDX, RBX, all these things. We actually have like 15 registers, right? So actually, to realize these 15 registers, we actually put like 15 registers in the put these 15 registers together to form a register file, which is like a small piece of memory. And it actually takes input. So it takes like address input. Because it's memory, it requires input address. So address input specifies which word to read or write. Okay. The register file holds value of program registers, RAX, RB, RSP, and so on. And the register identifier serves as address. So if you recall, in y86-64 architecture, we had 4-bit register specifier, right? So we actually to specify a single register, something like, if you remember, RA, RB. Each of these things is like 4 bits, right? Because we have some encodings. We have some encodings for individual registers. RAX is 0, RCX is 1, RDX is 2, and so on, right? So this register specifier is used as address to this register file. Okay. And then because we don't really use the 15th register, like ID 15, which is 1111, right? 1111 implies no read or write performed. Okay? So if you actually provide the address of 0F, I mean the F, or 1111, that means we are not really accessing those registers for read or write. Cool. And also it provides multiple ports. So what is port? So port is a pair of address and data. Okay, that's called port. So it's like address input for a pair of address input and data in out. Okay, this is called port. Okay, so let's say if you have like 2 ports, then actually you can read out 2 register values in a single cycle. If you have like 3 ports, you can read or write 3 register values at the same cycle. Okay? So in this example, we assume like a 3 register ports, 2 read ports, and this write port. So read ports takes register address, register number as input, and then generates the value as output. The red value will be the output will be the register value. And in case of a write port, it actually takes both register input and value as input, and then it actually overwrites the value of register with a new incoming value. Okay. So here is how register file works in more detail. For reading and for writing, it works differently. So for reading, it works like combinational logic. Means that if you actually provide an input, like a register like a number as input, the output comes out immediately. Of course, a little bit of delay. It's like combinational logic. So if you actually change the address input, then the output will continuously change. So in that regard, it's somewhat like combinational logic. So for reading, it works like combinational logic. The output data is generated based on input address after a little bit of delay. It's continuously changing. Okay? But for writing, it's different. It's like a register. So writing is happening only at the rising edge of the clock. Okay? So let's say you want to overwrite the value of register 2 with some other value. Then you actually have to provide the input address and input data to the write port, right? And then that value will be eventually updated, reflected in the register file only at the next rising edge of the clock. Okay? So in that regard, it's more like like a sequential logic. So here, if you actually, let's say you want to read out the value of register 2, then you actually, provide the address 2 to the address input, and then the output comes out immediately after a little bit of a delay. But for writing, let's say you want to overwrite the value of, this y, the register value, the register number 2 with the value of y, then this value is, let's say originally the value was x, then this value will be updated to y only at the rising edge of the clock. Okay, so it will be, updated the next rising edge of the clock. Eventually, it becomes like y. Okay, so to understand the difference between the two, for reading and for writing, they actually works a little differently for this register file. So here is a question: what happens if you try to, because we have multiple ports, we can access multiple registers at the same time, in the same cycle, right? But what happens if you actually want to do these 2 things together in the same cycle? So the question is, let's say in the same cycle, you try to read the value of register 2. At the same time, you try to update the value of register 2. Then how it's going to work in this example? Let's say the value of register 2 was originally x, and you want to overwrite the value with value of y. Then what's going to happen? Any guess? So let's say in this case, this one tries to access address value 2, and also at the same time, this one tries to overwrite the value with overwrite the value of register 2 with y. Then what's going to happen? 어떻게 할까요? 같은 레지스터를 동시에 읽으면서 쓰려고 하면 어떻게 될까요? 지금 원래 레지스터에 라고 치고 이 값을 y라고 업데이트 하려고 시도하면서 그 순간에 여기도 똑같은 레지스터를 읽는다고 하면 어떻게 될까요? 첫 번째 질문은 얘가 읽는 값, 얘가 보게 되는 값은 뭘까요? 이 경우에 얘가 읽게 되는 값은 x. 왜? 업데이트 되기 전이니까. 그죠? 그러니까 이게 업데이트가 되는 시점은 항상 라이징 엣지 오브 더 클락이잖아요. 그러니까 일단은 인풋 라이트 하려고 이게 라이트 리퀘스트가 들어와도 실제로 이 값이 업데이트가 되는 시점은 다음 클락의 라이징 엣지에서 업데이트가 되니까 지금 현재 그냥 읽으려고 하는 시점에서는 그냥 옛날 x라는 값이 그대로 읽히겠죠. 그죠? 근데 그러다가 만약에 라이징 엣지 오브 더 클락이 한번 지나가면, 그죠? 라이징 엣지 오브 클락이 한번 지나가면 그때는 이 값이 y로 업데이트 되겠죠. 그 다음에는 얘가 이게 y로 바뀌겠죠, 얘도. 그죠? 그런 식으로 생각하게 됩니다. Okay. All right. So let me briefly cover HCL a little bit because we already, looked at HCL, but let's take a look a little bit more, and then we conclude this lecture. So hardware's control language is very simple, toy-like hardware description language with like a C-like syntax. And it can only express limited aspects of a hardware operation, and it can only specify the combination logic, not sequential logic. So it's very simple, language just describing combination logic. There are two data types, Boolean and int. So Boolean is by convention we use like a small, like a lowercase name for Boolean like variables, small a, small b, and small c, and for like words, by default, because we have like a 64-bit architecture, by default this word is like has 64 bits long, right? And we use, by convention, we use uppercase A, B, and C for words data. And here's statement, Boolean, type small a is some like a Boolean expression, and integer value like uppercase A is some like integer expression. That's the statement. There's some like a Boolean expression such as like a logical expression, like a and, or, not. Those are very all the like logical operations. Word comparisons. We can actually compare like a value of two words to generate like one bit output, like a Boolean false, right? They may be equal, they may be greater than, less than, and so on. And set membership, this one is a kind of shorthand notation of this thing, because this is very common pattern. So we actually have like a shorthand like notation for this kind of pattern. So this one, A in parentheses B, C, and D means like either like A or A equals B, or A equals C, or A equals D. So you can write in this way, but to make it more like compact, we actually we introduce like a shorthand notation for this case because it's very common. That means A is one of the three, then that's true, right? For word expressions, we introduce case expressions, right? If you remember case, we actually have set of condition, colon, expression, right? And then we evaluate this like a condition one by one. It's like if you actually rewrite this code, it will look like this. If small a is true, then return large A. Else, if small b is true, then return large B. And else, if the third condition is true, then return C, and so on. Okay, that's how you interpret this expression. So it's kind of if chain, right? You actually start with if the first condition is true, then the output will be the corresponding expression. If the second one is true, then the output will be the second corresponding expression, and so on. Okay, so that's pretty much it. So I think we actually briefly went over the building blocks, to build simple CPU. And we also introduced HCL, the hardware control language, to describe those hardware component, hardware structure. Right? Any questions about this logic design part? Hopefully it's kind of reviewed to all of you because you have already taken logic design, as I know. Questions? Oh, by the way, I'm really sorry for this, but we have decided to give you the homework next Tuesday instead of today. The original plan was we're going to give out the new homework today. We decided to postpone it until next Tuesday. So we're going to give out, the third homework on next Tuesday. It's about, building the CPU, the modeling like a simple sequential version and pipeline version of the CPU. And we're going to give you 3 weeks because it's going to kind of a little bit long assignment. So we're going to give you 3 weeks, and it's about CPU design in logic level. Okay? 질문 있어요? Questions? Okay. No questions. Okay, now that we already know basically everything, now everything is in place. We know the ISA, instruction set architecture. We know the logic design. So now it's the time to combine the two. So we now build a finite state machine that can execute the instructions. Okay, so that's what you want to do. So before we do that, I'm going to go over because so many of you maybe just maybe don't really remember all the stuff necessary. So I'm going to kindly review of what we already covered before we start. Here, this is an instruction set we want to implement. Okay, we want to make a finite state machine that can take these instructions as input and it moves to the new like a state as a result of computation. Halt, knob, all these things. Conditional move. Also there are like 3 different types of moves, like immediate to register, register to memory, to register. There are 3 different types of move. Operation, like ALU operation, right? So like and sub, XOR, all these things. And jump, call, return, push Q, and pop Q. That's all. So these are all the instructions we want to implement. Relatively small set. So as I said, this one is like a simple enough for us to implement in hardware within a semester. And also it's complex enough to write some interesting programs using this assembly. Okay, so that's kind of nice balance between the two. Here, okay. So in this conditional move, there's like an XX thingy. So XX thing is basically condition. Like if it's 0, then it's like unconditional, like a register move, right? 2, 0 is like unconditional register move. This one. But if its second nibble is non-zero value, then it will be like conditional move, right? So move is actually happening only when this condition is satisfied after you're checking the CC, like conditional code. Okay. Also, in like OPQ, like an opcode, like an operation. So we actually have 4 different ALU operations supported: add, sub, and XOR, and they are encoded as 60, 61, 62, and 63. JXX is jump and branch, and again, if it's 70, if this opcode is 70, then that means unconditional like jump. Just it's like a go-to, right? And all these things are conditional, and for the rest of the cases, the program actually jumps to the target location only when this condition is satisfied. So that's the reason why it's called conditional branch. We also went over the building blocks. We went the combinational logic plus like a sequential logic, and we went over ALU and ALU, MUX, and comparator, whether this actually compares whether this two value is true or not. Also, the notation was, this like a dotted line means just one bit output, and like a thick line is like a word. So combinational logic actually continuously responds to input changes, and it's operate on data and used to implement control. Storage elements, they are stored bits, and we talk about register files. We actually implement these program registers using register file, and also like non-addressable register. This one is used for like a program registers, but there are like other registers as well. We're gonna also use like this register. Especially we're gonna use what is called pipeline register, which we're gonna introduce in the later lectures. So there's like a addressable register file, which takes address to access specific word, right? It's a register file, and also there's like unaddressable registers, which doesn't really have any like address. It's just register. And as you remember that this value is updated only when this clock rises. Clock make a transition to from 0 to 1, right? Also, hardware control language. There are data types, Boolean and int, and statements. All these things. We just like went over 5 minutes ago, so I'm going to skip it. Okay, so now we are ready. That's how we can put these things together. Here's the basic, like a very. So let me do it. So today and next time, I'm going to go over very simple, like a CPU called sequential implementation. So sequential implementation means, we basically every rising edge of the clock, we read one instruction. Okay, every rising edge of the clock, we read one instruction and execute that. In the next cycle, we read like a new instruction and execute that instruction. So basically, one instruction at a cycle. That's called sequential. And so I'm going to cover this sequential implementation today, next Tuesday, right? And then our scope of midterm. Okay. Following that, we're going to do optimized version of a CPU, which is called pipeline version. So in case of if you do pipelining, you actually execute multiple instructions together. Okay. So that's basically the plan. So today and next time, I'm going to go over sequential, like one instruction at a time, implementation of the CPU, which will be covered by the midterm. And after that, I'm going to go over the version, which takes a lot more effort to develop. So here is a very simple, like a sequential hardware structure. We actually first have to define state, right? Because after all, this is also like finite state machine. I mean, you have like a limited number of states. So it actually has, what kind of states does it have? So first, it has program counter, PC, or IP. Instruction pointer is the same thing. RIP, like instruction pointer, PC, program counter. They are interchangeable. They are like used interchangeably. The program counter is there. The program counter actually points to what instruction to execute this cycle, right? And conditional code registers, because we actually have to maintain the conditional code, like carry, 0, overflow, and so on. And register file, of course. Register file is there, and also memory. Okay, what kind of memory do we need? Because our programs, all this program and data is stored in memory. That's called like a program like a model. So we actually put the program code and data in the same physical memory, right? So we actually need but for now to simplify things, we assume there are two separate memory pieces. This one is the instruction memory, where we store the the program code, and let's say there's another a data memory here, and this one is for a data. So once you execute load or store instructions, such as a move, RM move. RM move is you copy from register to memory, right? Then data memory is what is being used. You actually copy your register value to data memory, not instruction memory, right? So instruction memory is kind of like a read-only memory. You can really write to it. It's just there to store some So that's basically, there are two pieces of memory, we assume. Of course, eventually, they will be merged into a single piece of memory in a memory hierarchy, but it's going to be a topic of the much later part of this course. So for now, let's assume we have two separate pieces of memory, which is one for instruction, the other for data. So also instruction flow. So if you execute the instruction, generally, the instructions actually follow a similar path to execute the instruction. So what needs to be done if you want to execute an instruction is you first read instruction at the address pointed to by PC. Okay, the PC register actually points to the next instruction to execute, right? So you actually read like your next instruction to execute from the location. PC actually, what PC points to. And you process through all these stages. There are like a bunch of stages, like a fetch, decode, execute, memory, write back. I'm going to explain what are all these things later, in a few slides later. And finally, you also need to update the program counter, right? So as a result of execution, you actually have to move to the next instruction, right? You have to update the program counter. So that's basically and repeat this process forever, right? Then actually, your program actually make progress. So here, let's say you think about, let's say you want to execute like an add instruction, add Q. Okay? So if you want to execute like add instruction, you have to first read the instruction from instruction memory, right? You have to read those like a 2-byte, instruction from like instruction memory, and then because add Q RA RB, you want to execute like this instruction. Right? Then first of all, you actually have to read this instruction code, like a 2-byte instruction from this memory, and then now you actually have to read this value of the registers, right? Let's say this RAX, this is like a RBX, and this one is RAX. Then what you have to do is you have to first read the value of RBX and RAX from register file, right? Once you read the value, read the instruction code, and read the value from register file. And then you execute this, you do actually add using this ALU, right? Here's the arithmetic logical unit, so actually put these 2 operands into the ALU, and then you compute the result. And then finally, you write back the result, the computed like value, the sum of the 2, back to the register file, right? In this case, you have to write it to RAX register, right? So you write it back to register file, and you also update the PC. So now the PC must be, PC plus 2, because this add Q instruction only takes 2 bytes. So the next instruction will be like 2 bytes away from the current location. So this PC will be updated with the PC plus 2, right? So that's it. I mean, that's basically how you execute this add instruction. So there are, generally, there are multiple, like 6 different stages in this case. First, you fetch the instruction. I mean, from the instruction memory. And second one is decode. So decode is you basically figure out what instruction it is, and then you actually read the necessary values, like a source operands from register file. Actually, that's what's done in decode stage. And the third stage is execute. So execute is basically you do some add or multiply or do some like AND or XOR, all this like actual like computation is actually happening in execute stage. And the fourth stage is memory. So memory is kind of you access memory for like a load or a store. Let's say your instruction actually requires access to memory. Maybe it could be like load, store, or maybe pop, push. They all requires access to memory, right? So in that case, you have to access the memory in this stage, like a memory stage, and actually you write back the value to the register file, because as a result of computation, you need to update the value of the register. Then that's actually happening in the write back stage. Finally, you update the PC register too. PC update to the next instruction. So in general, if you actually have just like regular instruction, you simply go to the next instruction, right? But if you actually have like a jump or a branch, you may actually jump to some like remote like location, right? So and that must be taken into account in your address calculation. So here is like an instruction, how this instruction is broken down. So that we actually, let's say we first name it first. So this like a yellow field is required, right? So any instruction at least take like 1 byte. This is opcode. This is called opcode. So any instruction actually has n is opcode. Even like a NOP or a HALT, those instructions do not take any operand, right? Even though they don't take any operand, they still have opcode. And this one's kind of required field, the first one. And we actually divide this opcode into two pieces. The first one is called ICode, like instruction code, and second one is called IFUND. It's kind of name. I mean, we just name it to make a reference. So this opcode is divided into two fields, ICode and IFUND. And also there may be like optional second like register specifiers. So in this case, may be followed by RA and RB. But this is like optional. And also, this one may also followed by another like optional field called like a D, the constant value. And this one is called val C. Okay, so we're gonna, when I refer to val C, that means the constant, D field in the instruction. It is a name. So we just name them like this. So instruction format looks like this. Instruction byte or opcode has two fields, like ICode and IFUND, and optional register byte actually has two fields, RA and RB. And finally, optional constant word is val C. Okay, that's the fields we actually have in any instruction. Okay. So let's start with very simple one first. So again, let's think about arithmetic logical operations such as like add, sub, and so on. So in this case, for individual types of instruction, I'm going to go over what needs to be done in each of these stages. Okay. So here, we actually have, let's say, add instruction RA and RB. Then, what needs to be done? So let's say you want to execute add Q, for example, add Q, RCX, RAX. Let's say that's the instruction. For example, you want to execute this instruction. What needs to be done? Or I kind of already explained about for this instruction, but let's review. So to execute this instruction in fetch stage, you actually have to read 2 bytes, right? Because this add instruction takes 2 bytes. And decode stage, you actually have to read operand registers. These two registers, RCX and RAX are those 2 registers in this case. You have to read these 2 registers in decode stage. And in execute stage, you perform add, right? You do the add, right? To add of the 2 operands, and also sets the conditional code as a result of computation, right? So that's what is done in execute stage. In memory stage, for this instruction, we don't have to do anything. We do nothing for memory stage. We just skip it, right? And right back, we update the register RAX in this case, register RAX with a new value, like a sum of the 2. And finally, we update the PC by incrementing this PC register by 2. Okay? So that's what it takes to execute this instruction. So here, is another view of how we do it. So you want to execute like OP-Q instruction. It takes like 2 register operands RA and RB. And in fetch stage, you first read the instruction byte, the opcode from the PC, the location at PC. So you read the instruction byte, and also you read the next byte too. So the next byte, and then you divide these 2 byte, the byte into 2 pieces, RA and RB. So, and by reading, these 2 bytes, you can actually set the value of these 4 fields, right? IFUND, ICode, RA, and RB. And also you compute the next PC here. Let's say val P is basically the next PC, and PC is PC plus 2. So how do you know that? How do you know this number? By inspecting opcode, you know that what will be the next instruction. How long is the instruction, right? That knowledge is hard-coded in your hardware. So if your CPU sees what the opcode of the instruction, knows what's the length of the instruction and what will be the next instruction, where the next instruction begins, right? So you compute the next PC based on this information. And in decode stage, you read these 2 register value, RA and RB, and then assign them to, let's say these 2 values are val A and val B. They are actually register value. You read from the register file. In execute stage, you actually perform the computation. You compute this value, val B op val A, And let's say the result is val E. So here E is basically, it's kind of execute stage, value produced in the execute stage. And also you set the conditioner code register as a result of this computation. And memory stage, as I said, do nothing. Nothing is done. And in write back stage, you update the value of RB register with val E, which is computed here, right? So you actually overwrite the value of RB register with val E, and in PC update, you update the PC with the val P, and val P is actually computed here, right? BC plus 2. Okay? 네. 네. 인스트럭션하고 인스트럭션 사이예요? 네. 네. 그런 구분하는 필드는 따로 없고요. 어떻게 되냐면은 일단은 예를 들면 이 경우에는 가장 긴 그냥 랭스를 가정하고 읽어요. 그러니까 예를 들면 우리가 지금 가정하는 인스트럭션 셋에서는 제일 긴 명령어가 10바이트짜리 명령어잖아요. 일단은 10바이트를 다 읽어요. 메모리에서는. 10바이트 읽은 다음에 맨 처음 업코드를 봐요. 근데 업코드를 보니까 이게 60이니까 예를 들면 ALU 명령어니까 2개 바이트밖에 필요가 없는 거예요. 그럼 뒤에 있는 나머지 바이트는 다 버려요. 그냥 읽은 거를. 버리고 이 2개만 쓰고 다음번에 또 시작할 때는 그 다음 2바이트 이동한 그 시점부터 또 10바이트를 다 읽어요. 읽은 다음에 그 업코드를 보면은 이게 몇 바이트만 실제로 필요하니까 그것만 읽고 나머지는 그냥 값을 버리고 이런 식으로 계속 읽게 돼 있어요. 그래서 그게 단점이에요. 사실은 이런 그 x86가 시스코 아키텍처인데 시스코 아키텍처의 단점이에요. 왜냐하면 시스코 아키텍처의 단점이라기보다는 variable length 명령어를 갖는 거의 단점인데 만약에 명령어 코드가 항상 같은 일정한 길이를 갖는다 그러면 굳이 이번 명령어를 디코딩하지 않아도 다음 명령어가 어디서 시작하는지 알 수 있잖아요. 근데 여기에서는 항상 업 코드를 봐야지만 다음 명령어가 어디서 시작하는지 알 수 있기 때문에 불필요한 시리얼라이제이션이 생겨요. 그러니까 앞에 명령어를 꼭 실행해야지만 뒤에 명령어를 실행할 수 있는 그런 게 있거든요. 그런 것 때문에 이제 명령어를 좀 더 자유롭게 이렇게 오더를 막 바꿔가면서 실행하는 그런 옵티마이제이션이 불가능한데 그런 게 없는 아키텍처들에서는 그냥 좀 여러 개의 명령어를 그냥 한꺼번에 읽어가지고 동시에 처리하기도 하고 이런 것도 좀 쉬울 수 있어요. 어쨌거나, 네. Alright, so in summary, I mean, what I just told him was, we don't really know. There's no marker or anything like that actually marking the end of the instruction. So we actually have read the entire like a 10-byte code, and then we first inspect the opcode, and we just consume the necessary number of bytes, and then discard the rest of them. That's what's happening. Okay. So you can actually formulate the instruction execution as a sequence of simple steps, like this, and these like simple steps can be actually shared by all the instructions in this architecture. So let's take a look at another example here. Executing rm move. So rm move is store, right? This is store instruction because we copy the value from register to memory. So if you want to execute this instruction, first fetch like a 10 bytes because it actually requires 2 registers as well as the displacement, which is constant 8-byte constant here. So you fetch like a 10 bytes and you decode because we need like 2 registers, right? We have to first read register RA and RB, and in the execute stage we compute effective address. So effective address means so if you actually use this like addressing mode, the memory location we want to access is RB plus D, right? That's the memory location you want to access, right? This is effective address. So in execute, because we have ALU there, in execute stage we have ALU. We use that ALU to compute the sum of these two, RB register, value of RB register and displacement. Okay? So in this stage we compute effective address, and that address will be used in mem stage, memory stage, to store the register value to memory, and we do write to the memory. And in write back we do nothing, right? So write back was we actually update register file. That's write back, right? But in this case, we write the value to memory, but there's no need for updating register value. So in write back stage, we do nothing. We don't do anything. And PC update, we increment the PC value by 10 because this instruction actually takes 10 bytes, right? And let's do the same here. We break down this instructions operation into small pieces. And what's happening in fetch stage? Again, we first extract those fields from instruction code. So you first read the first byte from the location at PC to extract ICode and IFUND, and you also extract RA and then RB from the next byte, and also from the next 8 byte we extract a constant value. So all of these things, they are actually extracted. You basically read like 10 bytes and extract those like a field from those like 10 bytes. Also, ValP is kind of computing like a next PC. In this case, the PC is PC plus 10. The next location is PC plus 10. In decode stage, again, we actually read these two register value, RA and RB. So let's say here, let's assume we want to execute RM move RCX 16 RAX. Let's say that's what we want to execute. So in decode stage, we read the value of RCX and RAX registers. That's what's happening. So in this case, this val A is actually holding the value of RCX. And this val B will be holding the value of RAX. Okay? In this stage, we compute the effective address by adding the value of val B and val C. So val B was the value of the register here, and val C was the value of the constant taken from the instruction, right? So in this stage, we perform an add to compute the sum of the two, and let's say that value is val E. In memory stage, we use this value as an address, val E as an address, and access the memory location pointed to by that like address, and update the value with val A. Let's say val A is actually the value read from the register file. And in write back stage, we do nothing, and in PC update stage, we update the PC with val P, which is PC plus 10. Okay. All right. So next instruction is popq. So popq is kind of another interesting case. So in this case, we in the fetch stage to execute the popq instruction, the fetch stage read 2 bytes, and in decode stage we read stack pointer, right? Because so what pop instruction does is you read a word from stack location pointed by stack pointer, and then copy the value into the register specified by RA, right? So let's say you want to execute popq RAX register. Then you first, in decode stage, you read like a stack pointer. And in execute stage, you increment the stack pointer by 8. So incrementing stack pointer by 8 means you actually pop it. I mean, you shrink your stack, right? So you increment the stack pointer by 8. And in mem stage, you read from old stack pointer. So you read the data from old stack pointer before you actually do perform increment the value by 8. And in this case, interesting thing is you need to in the write back stage you need to update 2 registers, right? The first one is stack pointer because you pop it RSP stack pointer needs to be updated. Secondly, you actually have to write the value that's read from memory into RAX register. So in write back stage, you write back these 2 registers, update the stack pointer, and write the result from memory stage to the register RAX in this example. So 2 writes will be done in this popq instruction, and finally you increment this PC value by 2. So here is a stage computation. You can break down this, pop queue instruction in the same way. You can actually break down into multiple smaller pieces. So here in the fetch stage, you read like an instruction byte, like opcode, and register byte to actually extract those like 4 fields: I code, I fun, RA, and RB. And also value P is like computed at PC plus 2. And in decode stage, let's say you read the 2 copies of the same like a stack pointer, because we actually need to update the stack pointer and also read this like a value from stack pointer 2. You read the basically same register, because we already have 2 like a read port in hardware, so it doesn't matter. You can simply read them twice using 2 ports. So val A and val B will actually have the same value taken from the stack pointer. Like a stack pointer value. In execute stage, you add 8 to one of the 2 copies. And in this case, let's say we select val B. Val B plus 8 will be, let's say, val E, become val E. This will be the new stack pointer value, right? Because you have to pop it, you have to increment by 8. So this is new stack pointer value. It's computed here. And then you read the value from the original stack pointer value, right? This val A is the value of the stack pointer before you increment the value by 8, right? This is the original stack pointer value. So you actually read from this memory location and copy it to the some, like, let's say this one is val M. And in write back stage, you do 2 write. First of all, you update the register, the stack pointer with the value E, like a val E, which is original value plus 8. This one is update the stack pointer. And second write actually update the value of the destination register, because if you have to execute pop, you copy this like the value read from the memory into the register RA. So you write back the result. Finally, you update the PC with the val P. 네. 이게 사실은 그냥 피지컬하게, 이건 논리적으로 그냥 이렇게 표현했는데, 사실은 그냥 꼭 2개의 값이 필요한 거는 아니에요. 그러니까 사실은 RA나 RB 중에 한 개만 있으면 그 뒤에 있는 스테이지에서 그 값을 이용해가지고 값을 플러스 8 한 값이랑 그냥 원래 값을 그냥 쓸 수 있거든요. 근데 그냥 왜 사실 이렇게 좀 중복적으로 할 필요는 없는데, 그냥 하나만 읽어도 상관없는데 조금 약간 그렇게 그냥 했어요. 왜? 좀 불분명한 이유로. 예. 그냥 사실 한 카피만 있어도 돼요. 2 카피가 필요하진 않아요. 이거 하는데. Any other questions? All right, so let's move on to move. How it works. Conditional move works. Again, C move, XX, RA and RB. It first fetch the 2 bytes, the instruction code plus register specifier, 2 bytes. And in decode stage, we read like this 2 register value, RA and RB. Actually, you know what? We don't have to read the second one. Only we need to read the first one, right? Because conditional move, we need to read like only one of the register, the RA. In execute stage, if the condition is not satisfied, then set the destination register to 0F. Okay? So originally, destination register is RB, right? Originally, destination register is RB. But in execute stage, what happens is you check the conditional code. Okay? And then this conditional code actually matches the condition XX here. If it's true, then you simply write to the original destination register. But if they do not match, let's say if let's say you actually put like an EQ here, C move EQ, that means this move will be happening only when this equality is actually holds, right? But let's say this one is not satisfied, this is not, flag register says this is not true, then you override the value of this destination register to 0F, which is basically no register. Right? So depending on the, check the conditional code and you selectively override the destination register to 0F if the condition is not satisfied. In memory location to nothing, write back, update the register or not, depending on the value of destination register. Actually, in write back stage, it just performs a write, but maybe this destination register may be overridden to 0F. In that case, it's not really actually updated. And in PC update stage, increment PC by 2. Let's say here how this stage computation works. In the fetch stage, again, we read instruction byte, read like opcode and register, specifiers, and also we compute the next PC. And in the decode stage, we read operand A from register file. And in execute stage, we first compute the value of the two. I mean, because the first value is RA, second value is 0. If you add them to, the value will be simply the original register value, right? And also you check the condition. The ifont, this like an XX part and this conditional code, you check them too. And if they matches, the condition is actually true, then you simply, just write to the original like a destination register. But if it's not true, then you change the RB value to 0F. So RB will be used as the register file that will be used as the destination for write back, right? So you overwrite the RB register to 0F instead of the original value. And in memory stage, there's nothing. In write back stage, you write the value of computation, this value of computation into RB register, right? But as you see here, if the condition was not satisfied, then RB, like a register specifier RB, must have been overridden to like a 0F, which is like a no register. So in this case, the write may or may not happening. It may not be happening depending on the value of this RB. Okay. Finally, in the PC's update stage, we update the PC with val B. So here, I'm keep repeating the same, more or less the same thing again and again. By now you know that even though we execute different instructions, their patterns are almost the same, right? They may selectively take some of these pieces and mix and match, but they actually can they are almost they can broken down almost in the same patterns, same like a building like smaller like operations, right? So that's how we can build a very common like hardware to use to execute like multiple different instructions. So let's go over to another instruction. Let's say jump. How jump is executed. So here, if you execute a jump instruction, this XX actually specifies a condition. If that condition is satisfied, you actually jump to the target. Otherwise, you fall through to the next instruction, right? That's how this JXX instruction works. So let's see what happens in each stage. So in the fetch stage, we first read 9 bytes because it actually it's like a 9-byte instruction, and increment PC by 9. And in decode stage, we do nothing because there's no need to read registers. And in execute stage, you have to determine whether to take the branch or not based on this XX, this jump condition, and flag registers, which is similar to the conditional move, right? So in the conditional move, we actually have to evaluate whether we're going to execute this move instruction or not, depending on the value of this conditional code and this XX field, right? If it matches, then we jump. Otherwise, we move. Otherwise, we don't. Likewise, in jump instruction, this condition is satisfied, then we actually jump to the target address. Otherwise, we simply fall through to the next instruction. So this is execute stage. We actually check the condition. In memory stage, we do nothing. In write back stage, we do nothing. And in PC update stage, we set the PC to the destination if branch is taken. Otherwise, just simply increment the PC if the condition is not satisfied. Okay. All right. So stage computation, JXX test. Again, we do the same thing. Read like opcode and also read this constant like a value address. And PC val P is like a PC plus 9 because this instruction takes 9 bytes. And decode stage, we do nothing. Execute stage, we actually check the condition, right? Whether this is true or not, based on the value of conditional code. And we actually generate like a 1-bit signal, CND. CND is basically 1 bit, like true or false, specifying whether this certain, condition is satisfied or not. Memory, do nothing. Write back, do nothing. And finally, in PC update, depending on the condition, like a CND bit, if it's true, that means this like a branch must be taken. Then now, if it's true, then actually we take the val C as next PC. Otherwise, we take val P as next PC. Okay, so this one is the target address, and this is fall-through address. Okay. So the basic idea is we compute like both address, like a target address and fall-through address, and choose one of the two depending on the value of CND, which is evaluated in execute stage. Finally, let's take a look at call instruction. So again, it's the similar exercise. So here we actually, it's again like another like a 9-byte instruction. It actually has opcode followed by 8-byte destination field. So we in the fetch stage we read 9 bytes and increment PC by 9. And decode stage we read stack pointer. In execute stage we decrement stack pointer by call instruction. What you have to do is you have to first access the stack, right? Stack actually pop like a return address from the stack, and then put that like address into the PC. That's what needs to be done, right? Oh, sorry, it's actually not true. I talk about return. So you actually have to push the return address, right, in the call instruction. You have to first push the return address into the stack, and then you update the PC with the destination address. So here in execute stage, you actually push the return address by decrement this stack pointer by 8. In memory stage, you write the incremented PC. So incremented PC means basically the next instruction, right? Incremented PC means the address of the next instruction to the stack, and you update the value. That's basically what happens in memory. Basically, you push it push the return address to the memory to the stack, and also in write back stage you update the stack pointer because now actually you have pushed the return address, and also in PC update stage you set the PC to the desk like this field. Okay. So here if you actually break down this like a stage computation. You start from fetch stage. You read this instruction byte and also extract destination address, and also compute the return, which is the next instruction. P9 is the next instruction, right? Val P. And in decode stage, you read stack pointer, and in execute stage, you decrement stack pointer by 8 for pushing this like a return address. And in mem stage, you write this return address. Return address is actually this one, right? The next instruction. So you write the return address to the stack. And in write back stage, you update the stack pointer with this like computed value here, like this val E. And in the PC update stage, you set the PC to the destination. All right, so time is up, so I'm going to stop here, and then I'm going to continue from the return instruction next time.